Okay, enthalpy. Enthalpy, we already know it's equal to internal energy plus PV. So from that, I'm trying to get to TdS is equal to the enthalpy minus the specific volume dP. Well, how do I get that? Well, I already know that the enthalpy is equal to the internal energy plus P dV plus dP V, or V dP. So from there, I could rearrange my terms, substitute this in there, and take this, substitute it in here. So this will be my equation number 2, which simply says I'm going to take get everything in terms of dE. dE is equal to dH minus P, the specific volume, minus V dP. Then take this, substitute it in here, and this term will cancel out with this, and I end up with this equation. Okay? Straightforward? All right, so moving on. Wait, okay. All right. Okay, so I need my specific volume. Let's define a specific volume, which is equal to my internal energy over dT at constant volume. My specific pressure is equal to my rate of change of enthalpy over dT at constant pressure. So these are just definitions of terms that we need to keep in mind. And we know that the internal energy is equal to what? Do you remember internal energy is equal to?
Cp dt.
Cp dt. So this is from my undergrad, I still remember that. Third undergrad, sorry. What about enthalpy?
Cp dt.
Cp dt. Okay, very good. So from those, I could go and use those equations, substitute it in my TdS equations, and what am I going to get? I'm going to get S2 minus S1, which we drove earlier, is equal to my integral of, yeah. We're done with this? Okay. My S2 minus S1, the rate of change of temperature over my Cv as a function of temperature over T, delta T, plus R, the natural log of the volume change. Now, where do we get all this? So this is one of the equations we have to actually know, and we're going to say it's isentropic, so we're going to take this equal to 0, and then rearrange our terms, and that's how we get our isentropic equations that we've been using inside the table. But essentially, where do we get this? Well, we already know the internal energy is equal to Cp delta T. We already know, what is ideal gas law? PV is equal to rho RT. Okay, so I have entropy is equal to, I'm expecting here what? Q over T. Well, Q over T, I already know the relationship relative to internal energy. Well, where did we just see that? Right here. Right? It's dE is equal to Q PV, or P delta V. So I already know my Q, P delta V. P delta V is right here. I can substitute in terms of my ideal gas law, get it in terms of specific volume, the integration because it already changed. This, well, I already have Cp, I had here U, but maybe just make it E, sorry. Make this E instead of U. It's internal energy. You're already familiar with that. Nobody corrected me there. It's nomenclature, but probably understand that that's where we
easier.
So you already know your internal energy.
The last thing.
And from there, you can substitute in terms of your E, in terms of Q, PV, and get your integration. Question? Rho or V?
Yeah, P equals
So, I'm sorry.
or PV equals nRT use the reservoir.
MRT.
Is in specific volume.
So it's P is equal to
Specific
rho
volume
RT.
is equal to, or yeah.
Okay? Correct that. So, I'm used to P equals rho RT in general form, but, so that's why rho is equal to M over V. That's how you get that. Any questions on this? Okay, so from this, I could just get the integral, which is 1 over t, and just have it in a natural log-like form, which is equal to cv t, well, assuming that this is constant, so let's take the cv as a function of, well, let me just say, write this. Assume cv is constant, not a function of temperature. So if it's not a function of temperature, then it's constant. I can take it out of the integral and do the integration relative to t. So I'll have s minus s1 is equal to Cv, the natural log of T2 over T1 plus R, the natural log of the volume ratio. And if I already know how to do it in terms of Cv, using the same TdS equation that we have right here, I could apply it for Cp, because I already know that enthalpy right here is a function of Cp. So from there, I could get the same exact equation for Cp, which is S2 minus S1 is equal to Cp, the natural log of T2 minus T1, and in this case it's going to end up negative, R natural log of volume over volume? Pressure ratio. And these are the two equations that I need to worry about. And actually we're going to say, well, what is the isentropic process? We reset the delta S to 0 and rearrange the terms, and what are you going to end up getting? The relationship of temperatures and volumes and pressures in terms of what? Yeah. So from there, you can say for isentropic process, for ideal gas, so ideal gas, T equals to rho RT or T, MRT, P is equal to rho RT. So ds is going to equal to 0. So if I take ds equals to 0 and set this equation equals to 0, rearrange my terms, well, and I know that gamma is equal to Cp over T. So if I rearrange my equations, my natural log is going to cancel out. So what am I going to end up with is T2 over T1. So this is where it's important for us because we're going to continue to use this, the specific volume ratio. gamma minus 1. So this is one equation that we have to use continuously throughout our engine in general. And the second one is T2 over T1 is equal to P2 over P1 to the power of gamma minus 1 over gamma. And the third equation is relating both, so taking the temperature ratios is equal and making the volume pressure ratio relation, which is P2 over P1 is equal to the volume 1 over volume 2 to the power of gamma. And gamma is equal to, at 300 degree Kelvin, gamma for air is equal to 1.4. Gamma for methane, CH4, is going to equal to 1.3. Gamma for argon is equal to 1.67. In the engine, what we're going to see later on, this gamma changes. So that's why another reason why we can't use the tables. The tables are for fixed gamma most of the time. These are the same relationships that you have in your isentropic tables. So it's assuming entropy is 0, and I want to use these equations. But generally you went in and you just used a variable of some sort and you extracted all the other variables. In this case, we're just going to use the equations directly because gamma is going to change. And at the same time, these variables are not going to be precisely the same values that you have in the tables as well. So these are going to be changing, and gamma is going to be changing throughout your engine because you're seeing a significant temperature changes. And we assume constant CP and constant CV, right? But in reality, they're going to change as well. And we're going to account for that. And you're going to see the difference of how much that change will induce as part of your calculations. Okay, so let's put all this together in a few examples right now, all the equations that we went through so that we iron it out through a few examples. Let's start with a simple one, which is a nozzle. Right here. I want to do as much examples as possible. So, isentropic efficiencies. So, what are we going to make assumptions in general for our engine? Question.
Did you say those equations are still valid for variable-specific heats?
It depends on, it's a good question, and we're jumping ahead of ourselves here when I mentioned it, but it's not valid if you're talking about getting really accurate measurements, or predictions, but you're gonna actually evaluate it in one of the homeworks. The difference between if I consider it constant versus a variable, and you're gonna integrate the CP, and you're gonna find out the difference. As long as you account for CP as changing at specific locations within the engine, rather than the interval of it, you're going to be okay in terms of how you're predicting the value. But it's a good question.
You can linearize it to make it accurate?
Yeah, meaning at different stations, you could use different CPs without the full integration, and yet be very close to the real answer if you would to integrate it directly. But we'll get to that, because once you add heat, which is heat of combustion here, CP changes drastically, and we have to account for it. Okay, but good question. We'll get to that. Isentropic efficiencies, well, what do we make as an assumption? We're going to make an assumption. So far, we're using our equations, 1D, one-dimensional, steady state. And we're going to assume that, well, the engines are most likely axial and it's gaseous based, so I'm going to ignore potential energy as well. So potential energy I'm taking out of my first law. And right now, I'm going to look at components. I still don't know gas mixtures yet. I have to go, well, I have to revise gas mixtures. I have to revise reacting mixtures, which you've seen in thermodynamics, but we're going to revise it next. So